In this video, we introduce the uniform distribution, which is the simplest continuous probability model. The key idea is that every value within a specified interval is equally likely. We denote the uniform with values C and D. C is the minimum value the random variable can take, and D is the maximum value it can take. Unlike many other distributions that have peaks or skewness, the uniform distribution spreads probability evenly across the interval. It is often used to model situations where outcomes are completely random within a fixed range. Here we focus on the shape of the probability density function for a uniform random variable. Because every value is equally likely, the density appears as a horizontal line over the interval from C to D. Remember that probability corresponds to area under the curve. Even though the graph looks simple, it still must satisfy the fundamental rule that the total area under the density curve equals 1. Now we determine the height of the uniform density. Since the graph is a rectangle, its area equals base times height. The base is the interval length, which is d minus c. Because the total area must equal 1, we set 1 equal to d minus c times height. Solving for height gives 1 over d minus c. This ensures the density is properly scaled to represent a valid probability distribution. This leads directly to the formula for the uniform probability density function. For values between c and d, the density is constant at 1 over d minus c. Outside this interval, the density is 0. This simple form is what makes the uniform distribution mathematically convenient and easy to interpret. Next, we consider the mean of a uniform distribution. Using the expected value formula and integrating over the interval from c to d, the mean simplifies nicely to c plus d over 2. This makes intuitive sense. The average value of something that is equally likely across an interval should be the midpoint of that interval. Now we look at the variability of the uniform distribution. The variance is d minus c squared over 12, and the standard deviation is d minus c over the square root of 12. Notice that the spread depends only on the width of the interval. The wider the interval, the larger the variability. One of the nicest features of the uniform distribution is how easy it is to compute probabilities. For any subinterval between a and b, the probability is simply the length of that subinterval divided by the total interval length. In formula form, the probability that x is between a and b is equal to b minus a, divided by d minus c. This works because probability is spread evenly across the interval. Let's summarize the key facts about uniform random variables. The PDF is constant at 1 over d minus c. The mean is the midpoint c plus d divided by 2. The standard deviation is d minus c over the square root of 12. And probabilities over intervals are computed using simple ratios of lengths. Keeping these formulas together provides a quick reference whenever you encounter a uniform model. In our first example, the clinic accepts blood samples between 8 and 10 a.m. and arrival times are assumed to be random. We model time after 8 a.m. as the random variable t, which is uniform with c equal to 0 and d equal to 2. To find the probability a donor arrives between 8:30 and 9 o'clock, we compute the length of that half-hour window divided by the full 2-hour window. This gives a probability of 0.25. In the second example, medication times are uniformly distributed between noon and 3 p.m. The probability that a dose occurs in the first half hour is the interval length, 0.5 divided by the total length 3. This yields approximately 0.167. Once again, the uniform distribution turns probability questions into simple length comparisons.